Hi, welcome to the last lecture in the Physics and Society unit. Today we're going to be talking about the renewable energy, the grid, and storage, and how this all kind of comes together to kind of take all the pieces that we have been learning about and put that in to give you into one thing and to help you understand the electricity system as a whole. So, you've probably heard us talk about the grid, or you probably heard someone talk about the grid. So the grid is simply just wires, substations, and transformers that transfer electricity from where it's generated to where it's used. So though that is a complicated system, it's just the transportation of electricity from one place to another. So you know whether you're using some sort of big power system like coal, natural gas, nuclear, or hydro, solar, wind, any one of those types of power, you're just basically transporting that to wherever it's being used. That's the grid. It is important to note that the grid does not store energy. It has, generally speaking, no storage capacity. So if you are using energy, that energy is being produced, generated someplace else. So you flip on your light switch, that's not accessing some sort of battery or something like that. It's basically somewhere a generator has had to work a little bit harder in order to turn your light on. So it's basically kind of this immediate thing. So no storage there. So if we're going to just, right, if we know that generators have to produce all the electricity that is being used when it is being used, then let's take a look at when it's being used. So the rate at which you use energy is not constant, right? If you think about it, we don't need as much energy in the middle of the night as we do in the middle of the day. So this graph over here on the right shows what time of day we use the most energy and what time of the year we use energy. So if we take a look at here, the spring and the fall, our energy usage is a bit lower, right? Um, and during the summer and the winter, right, it's a bit higher. Now, the winter obviously makes sense because you are doing more heating and cooling, and actually this one's kind of interesting because you can see the two bumps. So this would be when you wake up and everybody's heat turns on, and then you get home from work and all your heat turns on. The the yellow is right because of air conditioners. So whether it's the air conditioner in businesses or the air conditioners um, at home, those are using a lot of energy, and so that's or electricity. So that's going to put extra stresses on the system. So we have to meet all of these energy demands, and we need to meet them when they are happening. So, so basically, you have to have enough power capacity to be able to handle all of those. And in the Northwest, we have these, but we have a pretty moderate climate. So, we're not using a ton of heating. We're also not using a ton of cooling, as compared to like California or, Florida or Texas or something like that, right? Where they're using a lot more cooling. So, this would obviously kind of be more extreme in other areas of the country. So, right? So again, the grid doesn't store any energy; it just transmits it. So power generation needs to change to meet the demand. So renewable energy like solar and wind can't make the or can make this difficult because they aren't what's called dispatchable. That means that right, you can't adjust it to meet the demand. That's what dispatchable means, right? If you need electricity, you can't, and it's not sunny, you can't just like get that. Okay, and this can cause issues, right? Because basically, we got to have our generators up and running right there, and so if you have kind of these weird shaped curves, that can be problematic. And that's what the next slide is going to get into. So solar and wind energy doesn't always align with the entire peak. If you think about when solar and wind is going to give you the most amount of energy, that's probably in the middle of the day. That's when it's the sunniest. That's when when wind is blowing the most. So, you're going to be getting the most solar and wind in the middle of the day. Maybe 12 o'clock, 1 o'clock. something like that, right? But if you remember back to the energy curves, that's not when the demand is the most, right? The demand is the most kind of right here, about 7 o'clock, maybe 7 o'clock in the evening. And so, um, and so that kind of can cause some issues. So big power plants like natural gas, nuclear, and coal, you can't ramp those up very fast, right? So basically, they take a long time to get heated up and going, and they take a while to cool back off again. And so the problem is since you can't change the amount of energy they're producing very quickly, right? Or if you do turn it on, ramp it up pretty quickly, you're going to waste a bunch of fuel, right? Think about like driving your car, that if you're like really accelerating quickly, that's going to waste a lot more gas than if you accelerate kind of more moderately. And so these big power plants, they can't change the amount of electricity that they produce very quickly. So if we make that curve, if that curve ends up too erratic, right, with big changes, the energy, right, those power plants either can't meet that, which isn't really acceptable, or they need to start turning on way earlier. So what happens is that sometimes we end up not actually using the solar energy because these large generators have to turn on so early in order to meet that evening demand. This process actually uh, happens most often in California. So that's one of the places that we see this happening the most, simply because California has so much solar panel. All these people have invested in it so early that there's a lot of solar panel or a lot of solar panels. So there's a lot of solar energy. However, right, that solar energy drops off. In looking at the graph here, it drops off around 6 o'clock. But at 6 o'clock, the demand is actually still rising. So that creates a problem where if the solar power isn't producing anything, something needs to meet that demand, right? Otherwise, the lights would turn off because there's nothing producing that energy. So what needs to happen is, right, solar power can cover a lot of this demand in here, but it can't, you know, it can't ramp back up, because what happens is if you're meeting your demand with solar energy, then your total curve starts to go down. That's this dotted line here, because you don't need your nuclear or your coal or your natural gas right then. But then what happens is it has to ramp up really fast and right here to meet this final demand. And remember, they can't do that, or they at least can't do that efficiently. And so we end up wasting a bunch of energy in this really fast ramp up. And so what sometimes happens is they just simply continue to run at max power there, and thus throw away a bunch of the solar energy. And and so therefore it's not obviously very productive. So this is called the duck curve, simply because it kind of looks like a duck, though not in the one that I have here because there's so many things shown. But I'll this link for the YouTube video. I'll put that on the assignment page, and so you can take a look at it and watch that. It's only a short, like 2.5 minute video or so, and it's a really good kind of summary of this thing called the duck. So, so even though California is the only one that has this problem right now, other places are going to have it as well. With the prices of solar energy going down, that means more and more places across the U.S. and across the world are going to be adding solar energy. So this issue is going to become more common. Washington State is actually one of the few places that doesn't have this. Now we're adding a lot of energy, um, solar energy as we go, but this duck curve effect doesn't really happen. The reason is because we get so much of our energy from hydroelectric power, and hydroelectric power um, is one of the few things that's capable of ramping up pretty quickly. So as solar energy dwindles, come like 5, 6 o'clock in the evening, we're able to start letting more water through the dam, and therefore, um, you know, meet some, or and those can ramp up pretty quickly. So that's good. The other thing is it allows us to, especially in the summer, to store some of that water behind the dam, and therefore, we can only release it when we need it, and so that's better in terms of our water storage. Um, it also, right, as our population increases, our electrical demands go up, and so adding solar energy is good because it helps us, right? It helps us just basically generate more electricity. So we're not really seeing this issue in Washington. Solar energy is still really good in Washington. The other thing to think about is that it's not really having the environmental impact that it would in, California or other places across the state or the country, because it's just basically replacing hydroelectric power. It's not necessarily replacing natural gas or coal or um, nuclears, right? It is a little bit, but not to the extent as it would be in other places. And so it doesn't. It's also not quite as great in that sense as it is, adding this solar panel doesn't necessarily mean that's less coal that's being burned or less natural gas that's being burned. It's less water going through a dam, which is kind of good, but not as obviously good. Anyway, so how do we fix this, right? What is the solution? Now, the easiest solution, and it's not really, it's just part of the solution, is to decrease that peak, right? If you can bring the peak power, right? If you can reduce, right, it kind of looks like this. If you can bring that down, obviously that means we don't have to ramp up our energies as much. So one of the ways to do that is by pricing. So we don't do this in Washington, again, because it's a problem, but in California, they've done is they charge you different amounts of money for different rates for when you use electricity. So electricity at night is way cheaper than electricity at you know 5, 6, 7, 8 o'clock. And basically that's just to help reduce that top curve up there. So by letting me, like if people are aware that that's really expensive, they might choose to do things not during that time. So maybe you got to run your dishwasher or your washing machine, right? Choose to do that in the morning or late at night, and that'll kind of help out. Um, charge your electric car. Right? An electric car can charge whenever. Just have it turn on in the middle of the night. And charge during the nighttime, use energy, while we're not, when no one else is using energy. So that works out pretty well. So those are some ways that you can help reduce the strain on the electrical grid, or that they are reducing the strain on the electric grid. This is obviously not going to solve the problem, right? We would like to be in a space where we don't have to like really monitor when when we're using electricity. And there's some things you just can't move. Like you can't move when you cook dinner or when you wake up generally. And so there's just some things that we're not going to be able to change. So this is part of the problem. It's a really easy first step, but obviously, if we're going to really change this, we need to talk about electrical storage. So if we want to reduce, right, our reliance on fossil fuels, we want to burn less coal, less natural gas, less nuclear. You want to do more wind, more solar. You're going to have a way of storing the energy from solar, because the problem with wind and solar it isn't produced when you need it, and also it's not reliable. You have a cloudy day, you have a windless day, not producing any electricity. You're going to need to make up for that if you don't have some sort of power plant that can then take over for it. So as we think more about trying to become less and less reliant on those fossil fuels, we got to think about how are we going to store and we're going to add more and more solar energy. How are we going to store that? So that's the big problem that needs to be dealt with. So obviously, the simplest thing is a battery. It's not really the simplest, but that's how we normally store electrical energy. So battery technology is changing rapidly, right? We um, just in the last 10 years, battery technology has changed tremendously, especially with Tesla coming on the scene and making cars. But just think about your cell phone batteries, laptop batteries, those kinds of things. Um, you know, tool, your tool batteries, all of those things um, have come a long ways in a very short amount of time. So we're going to go through basically all the different options here of how we create electricity, or sorry, how we could possibly store it. So a bunch of these things are a lot of research is going into these right now, and there's a bunch of different options, and some of them are more feasible than others. And we're going to start with lithium-ion batteries. So lithium-ion batteries are the same thing that's in your cell phones, laptops, electric cars, tools, those kinds of things. Everything that was on the last slide. So it's basically, not a new technology. I mean, it is a new technology, but it's something that we have currently. It's just taking these smaller things, right? These smaller batteries, these ones that are in our cell phones, and just making it really, really big. Um, and so this seems simple enough, except that these are they're expensive, right? Batteries are expensive. Like, if you buy an electric car, the cost of the battery can, be at least like $10,000 or something like that, right? Or more. Probably in a Tesla, you're looking at probably more to 15 or $18,000 in just batteries alone, if not more. So, and that's just to make a car move, right? If you want to power your entire house or power multiple houses or power a city, we're talking about a lot of batteries and they're expensive, right? So Tesla is working on this. You can currently, you can currently buy what's called the Tesla wall. That's this picture in the lower right hand corner here. And they're basically battery packs that just go on the wall for, um, for uh, people with solar and that have solar panels. So the solar panels are producing electricity, and then it is being stored and then used by either the house or being sold back to the power company um, at that peak that we were talking about, right? That peak at 7 o'clock at night. So there are approximately about late eight or eight-ish, maybe more, large-scale experimental lithium-ion projects that could be used for the grid that are basically storing enough energy for tens of thousands of homes. So in examples would be in California, there's a this 30 megawatts, so that would be the rate at which it can charge and discharge these batteries. 30 megawatts, 120 megawatt hours, so that would be the amount of energy that it's storing, which is basically enough energy to store or to power 20,000 homes for 4 hours. Now that might not sound like a lot, but keep in mind that we're just trying to cover that curve, right? So if we can cover that curve, now all of a sudden that solar energy is being used, and now you're not having to power those 20,000 homes with a coal plant or a natural gas plant. You're able to power them with solar energy that you just stored earlier in the day. Another example, and this one's a Tesla one, and it is in Australia, and it is combined with a wind farm, and it can charge and discharge at 100 megawatts. So obviously significantly more than the California one. But then again, that's the rate at which energy can come in and go out, not necessarily how much it can store. It can store 129 megawatt hours, which is only slightly more than the California one. So this is probably in part because wind is probably able to produce electricity a lot higher rate than solar is, and so it needs to be able to take in and put out energy a lot quicker. So, so that was lithium-ion batteries. The next one for a storage option is what are called flow batteries, and these are new technology. We don't really, we're not really using these. You're definitely not putting them in your cell phone, just they would take up too much room. But they're not. They're definitely different than our traditional batteries. So flow batteries work by basically pumping a liquid of electrolytes through electrodes, um, and they usually have two different liquids, and they kind of react. I don't know a ton about how it works, other than they're basically stored in these liquids. Now, here's the cool thing: you want to make your battery bigger? Easy, just build a bigger tank so you can store more electrolytes. So this is probably one of the more promising options on the market right now, because of its expandability, because the models that we have right now, they use like a somewhat rare element, but they're producing or batteries or they're developing batteries that use more common substances, so therefore they're cheaper. We can build a lot more. So if you have things that are all the pieces are fairly cheap, you can then obviously make big. You can ramp this up and actually you know implement it and use it. So versus lithium-ion batteries, the materials that go into a lithium-ion battery are fairly expensive, and kind of rare, and so therefore, right, making this on a large scale isn't super cost effective versus this potentially could be. One of the more promising solutions is something called Primus Power in California. They've been producing these kind of box-like things, which are about 2 meters by 2 meters by 2 meters. They're using a zinc bromine solution, which is kind of cool because it can all be stored in one tank somehow. Um, but anyway, it's in this different battery technology and showing some promise in this kind of flow battery style. So onto something that looks a lot less like a battery. And this would be compressed air. And so basically what they're doing is they're using excess electricity. So when, solar panels are basically producing a lot of extra energy, they're then taking that energy and electricity, they're using it to produce compress air, and we're usually storing that compressed air underground. You then release that air pressure to run a generator and create electricity to handle those peak loads, in the 6 o'clock, 7 o'clock range. So there's actually, this sounds a little bit crazy, but there are actually plants in existence today that are being built. And so we're testing this out, we're trying it. Doesn't take up a lot of space because usually you're storing that underground. Um, But one of the biggest problems with these is that when you compress air, it heats up. And so that doesn't seem like a very big problem. Um, but the problem is when you release air, it cools down. So the issue is you compress all this air, you store it, and then when you release it, it's gonna cool down. And so that's a problem because you're releasing like a lot of air. And so it would just basically freeze up your generator because it's just so much cold air that your generator would basically just freeze and break. So that's a problem. So what they do is they compress the air, which heats up. They then take that heat and they store that somehow. I think in one case they're storing it in like some sort of rock or something like that, like gravel basically. And so they're taking that heat, they're storing it someplace. Um, so now you got your compressed air underground, you got your heat stored someplace else, and then when you go to release it, you just heat the air back up using, by like blowing it through the gravel, and therefore it's heated the air back up to where it should be. So when you release it, it's not freezing all your components. So that's one of the tricky parts of this is this heating and cooling things and keeping track of that heat, because otherwise you're gonna have some issues. So, um, so yeah, that's cool. It's not the most efficient process, but again, uh, we're just trying to avoid not throwing away energy if we can. So, um, another one, and this is probably the one that is the most common right now. I mean, I say that it is not common at all, but like we're just not storing, right? We're just starting to realize the need for being able to store energy, electricity. And um, so this is probably right, and this can store a lot of energy. And we have a couple of them quite a few across the United States. But keeping in mind that when I say it is the one that we're using the most, that we're really not using very much. Doesn't mean we're using it very much because we're really not storing energy on a large scale at all yet. So the idea behind pump storage is really simple. It's just like a dam, except in reverse. So when there's excess electricity, you pump the water up to your reservoir. So you take water that's down here at sea level or in your river or lake or wherever, and you pump it up into your reservoir. And then when you need the water, let it go down and right back down, and turn your turbine and generate electricity just like a dam normally works. And so does have a couple of issues. One is that it's got to be located where you would have areas where you have water. So you got to have a lake, got to have a river or something. And um, this little diagram here says a sea, but obviously there's kind of issues with using salt water. It tends to be really hard on things. So they're developing some models for a sea, but generally right now we're trying to use, like, do it in places where you have um, fresh water. So the other thing is you have to have elevation changes, right? This couldn't be used at all like in the Midwest because just it's flat, right? So if you have areas that are flat, uh, you can't really do this. So you gotta have elevation changes and water, presume hopefully fresh water to do something like this. Um, an example of this, kind of the bigger ones, I guess, is the Ludington pump storage, which pumps water out of Lake Michigan and stores it up, like 100, 300 feet, 300 feet or something like that, and up there, which is this picture in the lower right hand corner here. So these are cool. They tend to be fairly efficient given what they are. Right, 60 to 70% efficiencies. Um, right, you're losing water or you're losing some of your efficiency to turbulence in the water. So as you pump it up, it's just not 100% efficiency is sufficient to pump water up. And then also that water is going to evaporate when it's up there. So you just pumped it up and it evaporated. And so obviously, um, any water that's evaporated is energy you're losing. So got some downfalls there. It also takes up a ton of space. So um, right, like think about a battery. Batteries tend to not take up a ton of space. And so, like, if you were to try to store the same amount of energy that you would in a lake using a battery, it would take up way less physical space. So there's that. So it's called energy density. It has a pretty low energy density, which isn't great. However, right, it doesn't use any terrible chemicals like batteries and stuff do. So big plus there. It's very simple. Just we have a dam. It's not drastically new technologies. Um, so it's got some big pluses in its simplicity, um, but it's got some downfalls in that it needs to be in particular locations, and that it takes up a lot of space. One that I don't think we're using at all. It's just kind of one of these things that um, people are talking about right now is basically the same idea to pump storage, but you're using blocks and cranes. And so when you have extra electricity, they're raising these really like heavy concrete blocks and stacking them on top of this pile here. And then, right, when you need the energy, you then lower the blocks back down to the bottom and you generate electricity by lowering these heavy concrete blocks all the way back down. So it's just like pump storage, you're basically storing gravitational energy, but instead of doing it with water, you're doing it with these concrete blocks. Pluses would be that it could be done, closer to town, basically. Um, so closer to where energy would need to be done, or closer to where energy is being produced. So if you had like a wind farm, you could build one of these next to the wind farm. Oh, it's really windy there. It seems like that wouldn't be a great plan. Um, but it is just kind of an idea. It's again very simple. I don't know that they've actually built one yet, but it's just kind of a cool thought. And I think this is our last one here. So this one is storing heat. So we talked a lot about how you turn heat into electricity. Um, and we talked about this. I actually showed you this picture of this solar thermal thing, which is actually in Nevada. It's called the Crescent Dune Solar Energy Facility. And instead of using regular solar panels, it uses mirrors and shines its electricity here at this thing, which is actually, I think I said about water last time. It's molten salt actually. And then they run it through a steam generator, much in the same way that you would run water through a steam generator, except it's not steam, I guess. And so the other cool thing about this is that you can store the thermal energy to be used later. So even when the sun goes down, this plant could continue to function because, so if you see these, right, these kind of metal, shiny looking tanks here, those are full of heated, superheated molten salt, or right, and so they're storing that thermal energy to be to be used later. So even when the sun goes down, then they start using the thermal energy that's in those tanks to produce electricity as well. So in this case, right, this power plant could continue to run into 7 o'clock, 8 o'clock at night to continue to round off that duck curve. And so, right, that would be very helpful. We of course know, right, from learning about um, thermal generators that heat to electricity is not always the most efficient process, right? You're looking at 30 to 40%. So I'm not sure what this one runs at, but generally speaking, anytime you're trying to go from heat to electricity, um, that happens. So with that, thank you very much for watching all of these. I hope that you found this informative and interesting. And yeah, good luck. So thanks for watching and take care.